Hi, everybody. Welcome back. In this video, we're going to delve a little deeper into the TensorFlow Data API and learn how to use some additional methods available for creating data sets, either from data on the file system or from data that resides in memory. Up until this point, we've been using image dataset from directory, which is very convenient, but we're going to demonstrate how to use some additional methods for creating data sets that will provide a little more flexibility and some performance benefits. Data processing is a big part of computer vision and deep learning, and it's always good to have several options available for loading data. This is going to be the first in a series of 3 notebooks on this topic, and with each notebook, we're going to use the same model and the same data set to demonstrate each approach so that we can focus on the details of each method. Each of these notebooks contains many of the same building blocks as previous notebooks in the course, so we'll focus the discussion on the new topics and the associated code. So to get started, we're setting up some training and dataset configuration parameters. And in this section, we're going to download a version of the CFAR10 dataset that's been modified so that all the images are contained in their respective class folders. Notice that the dataset has train and test components. And in a situation like this, you would normally split the training dataset into train and validation components. But to keep things simple in this demonstration, we're simply going to treat the test data as the validation dataset when we train the model further below. And then here we're defining a function for the Linnet 5 model architecture. And so now we've come to the first section in the notebook where we're going to discuss how to create a data pipeline from data that resides in memory. And before we get into the coding details, it's worth mentioning that there's a 2-step process required to demonstrate this approach. The first step involves loading the CFAR10 data into memory and then creating a data pipeline with another function that we're going to define further below. If you're wondering why we also downloaded the CFAR10 dataset to our local system, the reason for that is to demonstrate the next approach where we're going to create a data pipeline from data that resides on our local file system. But for this first approach, we need to have the dataset in memory. So with that as a preview, let's take a look at the function that we'll use to load the dataset into memory. Since the CFAR10 dataset is available in keras.datasets, we'll use the built-in function to load it, just like we have with other datasets in previous notebooks. And then after loading the data, we normalize the images and convert the labels to a one-hot encoding. So now let's take a look at the next function called prepareInputPipeline that creates the data pipeline. The function takes 2 arguments, which are the images and the labels in memory that are returned from the previous function, and we pass those directly to the function from TensorSlices, and that creates for us a TensorSlice dataset object. So in effect, we're combining the images and the labels into a single object using the first dimension as the common element. And you can see that we've added the shape of the inputs and the output from the function call, just to be clear how the data is transformed. We can then apply several methods to this dataset object that are documented below to improve the performance and also shuffle the dataset. Notice that we're applying each function call in sequence, but there's another shorthand syntax that can also be used just the same, and we'll demonstrate that further below in the notebook. So now that we've defined both of these functions, we can load the datasets and create the associated pipelines for training and validation as shown in the code cell below. And then we'll proceed with compiling and training the model just to confirm that we've generated valid dataset pipelines. As you can see in the training results below, the loss and the accuracy look to be following the expected trends. So now let's move on to the next section where we're going to create a data pipeline from data that resides on the file system. And so for this purpose, we're going to use 2 different methods from the TensorFlow Data API. The first method, called listFiles, is simply going to create a dataset object that contains the path names to all the image files on the file system. Technically, this object returned by listFiles is a shuffled dataset object type, but it's worth mentioning that the various dataset methods that we're using all return dataset type objects that inherit methods from tf.data.dataset, and informally we'll refer to this object as a list dataset since it contains the list of file names. The next method that we're going to use is called map, which allows us to apply a user-defined function to each of the elements in the dataset object returned from list files. This is a little hard to describe without actually looking at some code, so let's go ahead and walk through this one step at a time. First, there's a couple of things that we're going to need further below. So here we're defining the class names for the CFAR10 dataset, and then here we're setting the root path to the dataset. This next code block is pretty straightforward. Here we're going to create train and validation list datasets by calling the list files method and passing in the appropriate path name for both the training and validation data. And again, even though the dataset is partitioned into train and test, we're just going to be using the test data as the validation dataset. And then here you can see we're printing out the first 5 elements of the training list dataset. And you can see that each entry is a tensor that contains a path name to each image file. And so that's all we're doing in this section. In this next section, we're going to define a function called processPath that's going to process each of the image files in the list datasets. This next point is important and not necessarily obvious, and in case you're wondering, the input signature to this function is determined by the structure of each element in the list dataset, which is a file path to an image file. So this allows us to write our own custom code to process each of those images that reside on the file system. So for each input file path, we start by reading the image file and then decode it from a byte string with a function called decodeImage. And then we'll convert the image data to a float32 tensor. Then to retrieve the corresponding label data, we parse the file path to retrieve the class name, which is the parent folder in each file path. And then compare the class name to the class names list, which returns a one-hot encoded representation for the label. And then to determine the class ID, we simply need to pass that to the argmax function. And so this function returns both the image and the label, which is exactly what we want. So now that we've defined this function, we're going to use the map method to apply the function to the elements of the data set. As shown in the first 2 lines below, each function call returns a map dataset object, and as before, we can apply all the other methods that are recommended to shuffle the dataset and improve the performance during training. Notice that we can string together these function calls with the syntax shown below, which is a little more compact than explicitly making the assignments in sequence as we had previously done. Also note that the main performance benefit for applying these functions is for the training data, which is why we've explicitly specified those for the training dataset. For the validation dataset, we're simply setting the batch size. And then as before, we're going to compile and train the model. And so let's go ahead and move on to the final section where we're going to plot the training results from both cases using the 2 different methods that we've demonstrated in this notebook. Since we used the same model and the same data set, you would expect the results to be nearly identical. But recall that there is a stochastic nature to the training process, and so there's some very subtle differences in the plots below. But the main focus of this notebook was to demonstrate the capabilities of the TensorFlow Data API to create efficient data pipelines. In the next notebook, we're going to continue on with this topic, and we're going to show you how you can use the sequence class in TensorFlow to create a custom data loader class that has a lot of benefits for handling more complex data. Thanks so much, and we'll see you next time.